Hello, welcome to Electronics Education. I'm Vincent Chang. Thanks for coming to the lecture. So in this lecture, I'm going to continue our lesson on the characteristic of practical operational amplifier. And we're going to focus on the input offset voltage. Input offset voltage. So let me start with the output. Look at the title. DC offset. So let me ask you, if now you see an ideal operational amplifier. If the op-amp is ideal and we connect the two input terminal to the ground, then what kind of output this circuit will generate? Zero output, right? So that's the concept from the common mode rejection. Common mode rejection. Again, if both input are connected to the DC ground, the common zero voltage point of the two power supply, and then the output will be zero. This is the ideal case. But in reality, for a real operational amplifier, for a non-ideal operational amplifier, the output won't be zero. So this kind of non-zero output voltage is called the output DC. Okay, this is the DC problem. So I'm not talking about AC. So this is the time-independent problem. This is the DC problem. Okay, so one of the DC problem that a real operational amplifier faced is the offset voltage issue. So the real op-amp, the output won't be zero. So this kind of output is called the output DC offset voltage. Output, look at the title, DC offset voltage. So you might be wondering why this happened. All right. So before we talk about the why, then let's just look at this. The 741, the operational op-amp manufactured by Texas Instrument. So there are two pins. It's an 8-pin package. So there are two pins says the offset nullify. So which means if you want to eliminate or nullify the offset voltage, you can actually try these two pins. You can actually connect to this two pin will help you nullify the offset voltage, eliminate the offset voltage. So I said, you might be wondering why this happened, the offset voltage happened. So let me, because I have to find the balance again. So I assume you don't have any strong background on the analog integrated circuit. So this is not so we cannot go deep, okay? But on the other side, I don't want to just move forward and solve some of the easy task, okay? So I wanted to still get some insight out of this without going too much detail or around the analog integrated circuit. So this is what I'm going to do. So you saw this before, right? This is the microscopic view of a real operational amplifier. And there's a stage called differential amplifier. It's the input stage. The differential amplifier is this. The blue corresponds to the blue, okay? So now, there are actually two reasons cause the offset voltage. The first reason is what we call the systematic offset. In other words, the circuit is designed this way. The circuit was born when the offset exists when the circuit was born. All right? So that's called the systematic offset. And the second reason is because the manufacturing imperfection. Because, so I would I will teach this in a fundamental analog electrical circuit and try to solve the input offset voltage for a differential amplifier. So in that case, I will assume sort of the device mismatch or load mismatch. So that's because the mismatch from the two sides for the input differential amplifier. So two reasons. Number one is systematic offset. The other one is the mismatch of the differential amplifier. So because of these two reasons, when you connect these two input terminal to ground, DC ground again, and then the output voltage, look at the right hand side, will not be zero. The output voltage will not be zero. This kind of output voltage is called the DC output offset voltage. So the first part of this lecture, I want to introduce the reason for the offset voltage. So now I'm going to talk about the second part of this lecture, which is the modeling of the offset voltage. And to explain that, to illustrate the model, I use the two illustrations. Here comes the first one. And the left-hand side is the case, right? Is the problem. So now how are we going to analyze this with a closed loop or operational amplifier circuit? So we need a model. So on the right-hand side is the model. So model of what? The model of a real amplifier where the offset is present, where the offset issue shows up. So then the model says, let's assume a non-ideal operation amplifier. A real amplifier is composed by an ideal operation amplifier plus an extra voltage generator, an extra voltage source. And that voltage source is called the input offset voltage. So picture this in your mind. So you can close your eyes and picture this in your mind. So what's the issue? The issue is when both inputs connected to the ground, and then there exists an output voltage there, output voltage there. So you think about this. You imagine that non-zero output voltage comes from a source called input offset voltage. And that output voltage, so that output voltage is created by a differential signal, a differential voltage, and going through the operational amplifier and multiply by the differential gain. So this is the first illustration. I'm actually explaining this equation. That's also the definition of the input offset voltage. Again, let me repeat that. So we think about that VO, the output DC offset voltage is generated by an imaginary input offset voltage, and trying to going through the op-amp has to be multiplied by the DC gain. Okay? So this equation has to be it's better to be interpreted by the input offset voltage times DC gain. This is not called AO, okay? This is A0. The subscript is called 0. It means the DC. The omega equals 0. All right? So offset voltage times the DC gain equals the DC output offset voltage. That's the first illustration. So sort of it's the internal force. It's the to reveal, to stands for the degree of the mismatch of the differential amplifier. So you can imagine this. And then the second illustration is this. So actually, you can measure this. This is the internal force by the external applied voltage. So you apply voltage. So you see the polarity on the right-hand side. You see positive, negative, negative, positive. So it's the constructive or destructive. It's try to add more or try to cancel. It's try to cancel, right? So when you apply, then the VO will go down from the original offset level, and then will go down. So what if we apply a voltage just to cancel down the input, the orange one, then the output will be 0, right? So the second illustration for the input offset voltage is actually you apply a voltage. You apply a voltage, try to eliminate, try to cancel out, try to balance out the internal force. And when you see the output voltage down to 0, that corresponding input voltage can be defined as the input offset voltage. So two illustrations for, one is more for the internal perspective. The other one is more for the external. So now here comes the third part. What's the effect when you do analysis? See, the left-hand side shows a non-inverting amplifier. Now the op-amp is not ideal. It suffers with the offset issue. So now I'm asking you to analyze this circuit to be more specific than what's the DC output voltage in this case. So I said, what's the DC output voltage? Which means we can let the input signal to ground. We can force the input signal to ground. Purely consider the output voltage generated by the input offset voltage. So let's just replace the op-amp, the real op-amp, by the model I mentioned 5 minutes ago, right? So a non-ideal real op-amp is composed of an ideal op-amp plus a source. That source is called input offset voltage. That's easy. The answer? Non-inverting amplifier, right? Virtual short. Then what? Times 1 plus R2 over R1 is this. So this is the good news or bad news. Of course, it's a bad news. Why? Because now you imagine, you expect the DC is 0. So then you can have this kind of swing. And in the previous series, I was talking about the ceiling voltage, right? So you're going to hit the ceiling, right? And then sometimes even cause the distortion. So if you don't want to suffer the distortion of your output signal, then you have to limit your swing. So your output signal swing is limited. So this is not the good news. So let me ask you another question. For this, what's the output offset voltage? This circuit is similar, right? So it's from the non-inverting, it's similar to the non-inverting, but plus one capacitor, CC. So what's the output voltage? DC voltage. So this is what we call the offset suppressed. If you do the analysis, according to the previous analysis, it's going to be the offset voltage times to this part, R2, divided by this part, right? But what's the resistance of the green part? You have to ask. You have to ask me back. Sir, what's the frequency? I never changed the frequency. I said in the beginning, this is the DC problem. The omega equals 0. So only one frequency makes sense when we talk about the offset. It's DC. So the DC resistance of the green structure is infinite. the DC resistance of the green structure, the green block, is infinite. So effective DC resistance of R1 is actually infinite. So in this case, the offset voltage, the internal force won't be amplified. It won't be amplified. So this is the offset suppressed. But there's also a downside for this circuit. If you have ever studied the lecture I talked about before, this is actually a high-pass filter, right? High-pass filter. So for this, if the signal frequency is low, then this circuit, if you talk about the amplifier, this will pose a limitation for the low frequency amplification. Okay. All right, but anyway, I just give you an idea that there is some scheme or ways to eliminate, to suppress the offset voltage, something that you can think about. In the next lecture, I'm going to talk about another DC issue, DC problem, which is the bias current. I hope see you there. So thanks for watching